When class ended, we were talking about finding the slope of a curve if we have it in parametric equations. And we were looking at this problem. And let's just look to try to find dy dx at t is equal to pi over 4. And when t is equal to pi over 4, we in fact are sitting right here on the graph at the ordered pair 1 over root 2, 0. The other thing that we did was we discovered that since we were using parametrics, x is cosine of t and y is cosine of 2t, that we in fact could write this in rectangular form, since we could write our y value as cosine we know is 2 cosine squared of t minus 1, so y becomes 2 x squared minus 1. So if we wanted to find the dy dx at, well, we know this is where x is equal to 1 over square root of 2. Well, we could just take the derivative of our y value, right? That's the derivative with regard to x of that 2x squared minus 1. And that's going to give us 4x at x is equal to 1 over root 2. So we know that the slope of the line is 4 over root 2, which becomes 4 root 2 over 2. So the slope of this line right over here, according to our old methods, is 2 root 2. Seems kind of reasonable. Here's one other way to look at it. Another way to look at it is that we had found the velocity vector. And in fact, the velocity vector that we found was, again, velocity vector is just the derivative of the x component and the y component, so that becomes negative sine of t times negative 2 sine of 2t. And we, in fact, look for the velocity vector at pi over 4. And what we came up with was negative 1 over root 2 and negative 2. And the question is, what's going on with that? We know that if we have a velocity vector, well, velocity is the instantaneous rate of change. And what we know is that at this point, the instantaneous rate of change for the x is negative 1 over root 2. The instantaneous rate of change for y is negative 2. So at this point, one way that I could imagine this is that our y value, so I'm going to say our delta y with regard to t, but our delta y right now is going to be negative 2. And our delta x for some particular value of t is going to be negative 1 over root 2. So if I'm going to look for the slope of this line, I can think of it in terms of the slope of this rise over run. So I might be able to think of the slope of that line, so dy dx, right, change in y over change in x, dy dx, as negative 2 divided by negative 1 over square root of 2. I'm going to multiply top and bottom by root 2 over root 2, which gives us just 2 root 2, which is exactly what we came up with a little bit earlier. Okay, so we could do that. Here's a third way that we could do this. I'm going to go back to when we rewrote this as y is equal to 2x squared minus 1. And what I found was dy dx. And it seemed perfectly reasonable because here's why it's written in terms of x. But suppose I wanted to find dy dt. And this goes back to the chain rule. You would very reasonably look at this and you would say, that's kind of crazy. We don't even have a t in there. And the only way that this makes sense is if x is some function of t. So if we were going to use the chain rule, well, dy dt would have to be, well, our derivative of y with regard to x, but then would multiply by dx dt. In other words, if we want to find y prime of t, that's going to be y prime of x times x prime of t. So if we go back to this, though, again, nothing more than the chain rule, I could just rewrite this. So I'm, in fact, looking for dy dx, and I'm going to divide both sides by dx dt. So what I end up with is dy dx is going to be dy dt divided by dx dt. And this, in fact, is the formula we're going to use when we have parametric equations. Whenever we're looking for the slope of the line, it's going to be dy dt over dx dt.